So now let's move on to thinking about electric fields. So we've seen how previously things that have built up a charge on them will experience the electric force. So positive things will repel positive things, negative things repel negative things, and positive and negative charges attract each other. That's all well and good, but is there another way of thinking about this? Is there a better way of actually trying to work out the force experienced by charged particles? So what is this resultant force in a charged object? We're going to see later, it's very simple when there are just two involved. Just as we saw for two gravitational masses, it's easy to work out the force of attraction between them. We can do the same kind of thing with charged particles. But what if we've got more charged particles? Or what if we're not entirely sure kind of what we're dealing with in terms of we haven't got two charged particles, but maybe we've got a charged surface and a charged particle, something like that. Maybe there's an easier way to do it than just, or a better way to think about it rather than to just think of, the forces between two objects. And so what we do is we use the concept of a vector field again. Remember, we did this for gravity. We said that a vector field is essentially every point in space has a vector associated with it, and that vector tells us how, for gravity, it told us how a mass would move in that field. And so this is basically what we have for electric fields as well. These are just a couple of examples of vector fields. These definitely aren't the one and only vector fields experienced by charged particles. This one is actually something that a positive, this would be the vector field, or rather the electric field generated by a negatively charged particle. This is not a vector field associated with any sort of charged particle, but they are both examples of vector fields. The idea that you have a vector for every point in space, and that the size of the magnitude of the vector tells you how strong the force is at that point, and the direction tells you where to go. So a charged particle at this point, or rather just in general, we're not going to talk about charged particles here, we're just going to talk about vector fields in general. A particle here would experience a force in that direction, and it wouldn't be as strong as the force it would experience here, but it would be in a different direction. And the same thing here, a particle here would experience a force like that, going that way, and then so on and so forth. So these are examples of vector fields. And so what we're going to say is that all charged objects generate a vector field. The idea is every charged object creates a field around itself called its electric field, and that electric field tells other charged particles how to behave, how to move, or what force they experience when they're in the field around this charged particle. So all charged particles generate an electric field, and so that's basically every single point in space has a vector associated with it, and that vector tells you the force that a particle experiences at that point in the field. So how do we demonstrate this? So for gravitational fields, remember we said that maybe we had a mass in the center here, and the arrows told us told us the force that a mass would experience. But it's a bit more difficult to do that with charged particles, because remember, for charged particles they can be positive or negative, and whatever force a negative particle would experience is the opposite to the same magnitude but opposite sign to the force that a positive particle would experience.
Hey guys. To continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.